back to the series. The security vulnerabilities are finally out of our application. In this video, we'll make it so that Alice and Bob continue to play against each other until there's a clear winner. This means if there's a draw, Alice and Bob will keep playing. All of the details about playing the game and the interfaces of the players will remain the same. The only thing that's going to be different is the order the actions take place. Currently, the steps are Alice sends her wager and commitment, then Bob accepts the wager and sends his hand, and then Alice reveals her hand. That's the end of the game. But now, since players can submit many hands under one wager amount, we'll need to change some of the steps. The new steps will be Alice sends her wager, Bob accepts the wager, Alice sends her commitment, Bob sends his hand, and then Alice finally reveals her hand. If it's a draw, we return to step 3, where Alice sends her commitment, the commitment to her new hand. Otherwise, the game ends. Let's make these changes to our program. First, we'll have Alice send her wager and deadline, and then commit it. We declassify the wager, we declassify the deadline, and then publish them, along with paying the wager. We haven't committed the hand yet, so we'll remove this unknowable statement for now. There's nothing Alice has secret at this point in the application. The next step is for Alice to accept and pay the wager. He won't play his hand just yet. And if he doesn't respond in time, then the tokens in the contract will go to Alice, just like before. Now for Bob's step, we won't commit it to the network just yet. It's at this point we want to start the repeatable section of the application, where each participant repeatedly submits hands until the outcome is not a draw. In normal programming languages, this would usually be implemented with a loop, and that's exactly what we'll do in Reach. If you remember, we previously used loops to generate and test possible scenarios for different outcomes and hands. However, the loop we'll use here is a while loop. This is another common construct in programming, and typically it looks something like this. There's a keyword while and a condition in the parentheses. While the condition is true, we execute the body of the while loop. That's in the curly brackets. Inside the curly brackets, something needs to happen so that eventually the while loop condition is false. The false condition is what allows the program to exit the loop. In this case, we have a variable called x, and while x is less than 5, we increment x by 1. When x equals 5 or is greater than 5, we exit the loop. Now doing something like this requires x to be malleable, to be changeable, so we can set it to a different value. Most of the time, this works in a given programming language, but Reach works a little differently. In a Reach program, everything is unchangeable. It's constant and static. We set a value for a given variable and it cannot change. However, as we see here, while loops require the value of a variable to be changed. The condition needs to be affected at some point so that it can eventually be false. This means in Reach, while loops are the exception. They introduce variable binding, which allows the value of a variable to be changed in Reach. Another thing to note is that due to automatic verification, we must make a statement about what properties of the program are unchanged before and after the while loop's execution. These are called loop invariants. This is a common computer science concept you may have heard of before, but if you haven't, I encourage you to look at the resources linked in the description. The last thing I'll mention before we implement this while loop is that loops can only occur inside of consensus steps. That's why Bob's transaction was not committed. We need to remain inside of the consensus to start the while loop. This happens because all of the participants must agree on the direction of control flow in the application. Let's try it out. First, we'll create a variable called outcome, and we'll give it the value draw. This will be used in the condition of our while loop. While the outcome is a draw, we'll want to continue the game. Before creating the loop, let's make a statement about what should remain unchanged before and after the loop's execution. This is an invariant. We'll want to confirm that the balance in the contract is twice the wager, meaning both Alice and Bob have submitted their tokens and have not taken any tokens out. We'll retrieve the balance and make sure it equals twice the wager. We'll also want to confirm that the outcome, no matter what it ends up being, is a valid outcome. We can add this to our invariant by using two ampersand signs. Both the balance equality and the isOutcome function must be true in order for the program to compile. The double ampersand sign is another common programming construct. It's a way of evaluating two true or false statements together to create one statement. In this case, both statements must be true in order for the invariant to be true. If either is false, the invariant will also be false, and the program will not compile. We call this ampersand sign a logical operator. It operates on true-false statements to create a new true-false value. Now with that out of the way, let's create the while loop. In the body of the while loop, let's play the game. We'll start by committing the last transaction. We do this because the while loop has to happen within a consensus step. Then we'll have Alice commit her hand. Just like before, we'll confirm that Alice's hand is not known to Bob before Bob submits his hand. Then we'll have Bob submit his hand. Once Alice and Bob have submitted their hands, we'll reveal Alice's hand. To end the loop, we'll modify the variable used in the condition, outcome. We'll set outcome equal to the winner of the hands. So that's Alice's hand and Bob's hand. Then we'll close the loop with continue. And we'll delete any of the extra stuff from the bottom. Now, unlike most programming languages, Reach requires that continue be explicitly written to end the loop. The body of the while loop is pretty similar to our implementation from before. The only difference is that the wager is separated out. Let's finish out the program. Since the outcome can never be a draw, we'll assert the outcome is either Alice or Bob winning. Here, we use another logical operator to combine the true-false values created from the outcome comparisons. As long as the outcome is A wins or B wins, the assertion will be true. Only one of these comparisons has to be true versus both, which is what we saw before with the and ampersand. The parallel bars stand for the or operator. One of the two comparisons must be true in order for the whole thing to be true. Otherwise, it's false. With the outcome determined, we'll transfer the winnings and commit the transaction. We'll use the transfer function, multiply it by the wager, And if Alice wins, we'll give it to Alice. Otherwise, we'll give it to Bob. Since there has to be a payout, we can simplify the logic from before. Let's run the program. And we'll need to remember to use relative time for those deadlines. Let's save it and run it again. Alice wins on the first round. Let's run it again. And we get a draw. Alice and Bob both play paper, and then they play another round. They keep playing until one of them wins. In the next round, Alice plays rock and Bob plays paper again. So this means Bob wins, and Bob gets the tokens in the contract. With the changes we just made, our game will always result in a payout. In the next lesson, we'll show how to exit this testing mode and turn this application into an interactive rock, paper, scissors game with real users. Thank you again to Algorand and Reach for sponsoring the series. If you have any questions about blockchain development, please join me in the Reach Discord in the Days of Blockchain channel. I'll see you next time, and happy coding.